Thank you, David.
Oh, can you put on the microphone?
Yes. Jesus.
Other way around.
Yeah. I think it's working.
I think.
Fine. Thank you very much. Yes, so I'm Daiane. I'm a research associate at Imperial College London. So I work with David, that's here as well. So in my talk today, it will be about checkpoint schedules for adjoint solvers. So I start to talk about adjoint. What's the adjoint? Adjoint-based gradients is a well-established approach for compute gradients in PD solutions. So we have applications and many areas of engineer as topology optimization, solving inversion problems, flow control. In this kind of problem, and the literature, the people want to compute a gradient of a functional with respect to some contour parameter. So here, for instance, we have an example, have a functional. We want to compute the derivative, the gradient of this functional with respect to some contour parameter. We have an example where U is satisfies a partial differential equation, in this case, a nonlinear Burgers equation. So when we compute an adjoint-based gradient, we have this kind of expression. So F is residual of the forward solver, in this case, Burgers equation. We need to compute the derivative. We have a dependence of an adjoint state. And when we are solving a time-dependent problem, we have this kind of time sequence in the sequence of the adjoint system. So basically, we have a forward solver. We run for a range of time steps, and then we need to compute the gradients. And the gradients, I'm using adjoint methods. And when I use adjoint method, I have to run the gradient, the adjoint method, backward in time, which means I have to solve my forward until the find out step, and then I back running the adjoint to get my the gradient of a functional with respect to some contour parameter. And I have this kind of structure here. So, which means I start the adjoint at the latest step of the forward solver, and then I have to compute the derivatives, which means I have to save data. And that can be very expensive for large simulations, for instance, seismic imaging or flow control. I have a large scale of simulations. I have a large number of time steps to solve. That's memory expensive. So one way to manage this memory usage is using checkpointing. So checkpointing, basically, we can run some essential, we run the forward solver and we save some essential time steps. Checkpointing is given by a checkpoint algorithm. So the checkpoint algorithm gives us some instructions as save only sometimes of the forward step. For instance, in this simple case, this simple example, we have the forward solver here. It's not working. So we have here these time steps that advance the forward solver here, and then the checkpoint algorithm says save only the first step. I don't have to save every time step. I want to manage the memory usage, and then at the final step here, I back and compute the adjoint first step here. Right, I want to compute the second step of the adjoint. I don't have the data. So I restart the forward solver here at step 1, and then I compute the adjoint until the final step. So with checkpoints given by some checkpoint algorithm, I can save memory for this kind of problem. We have a number of checkpoint schedules in the literature. So the first well-known is revolve. So it was first introduced in 2000, and with storage only in run, which means it store the forward, some steps of the forward data in run. We have also checkpoint algorithms with mixed storage, run and disk. We have a diversity of algorithms, checkpoint algorithms in the literature, and they depend. These algorithms depends of the solver. For instance, if I am a linear solver, I can recompute the forward as here, recompute the forward here at this step, and that's fine. But for nonlinear problem, recompute a forward solver is expensive. So maybe it's better to use some storage instead of to recompute the forward solver. I store on disk. Maybe it's cheaper than recompute the forward solver. So, right. You, for instance, you are using Phoenix and you have different solvers and you want to solve different optimization problem. You have a solver with nonlinear forward equation and have a linear equation. And you want to use different checkpoint approaches for these two kind of problems. So, and it's difficult because maybe you have a checkpoint algorithm in some code or in different languages, and so it's difficult for the user, for instance, to change the checkpointing or implement, so there is some time or need some expertise to deal with this kind of problem. Thinking this kind of problem, we have checkpoint schedules. Checkpoint schedules is a Python package, so that provides checkpoint algorithms for adjoint solvers. And checkpoint schedules was thought like to be independent of the checkpoint algorithm. So we can have different checkpoint algorithm there, and we have basic instructions and checkpoint schedules, and you can use different checkpoint algorithms and switch without to recode your solver. And that's good for the checkpoint schedules was thought to be good for the L4s as well. If you are thinking to propose, to implement a new checkpoint algorithm, you can use checkpoint schedules and add your algorithm there. And we have the basic instructions to deal with our checkpoint algorithm. So in checkpoint schedules, we have a number of checkpointing, revolve, and storage only in run. We have mixed storage approach. We have so we have a diversity of algorithms there. Checkpoint schedules is independent of, as I told you, is independent of checkpointing algorithm. So we have basic instructions there, and so make it for you, the user, easy to switch between the different checkpointing according your solver. You can find, so we can install, it's very easy. We can install checkpoint schedules. We have a number of checkpoint algorithms here. The documentation is available in Firedrake project. We have also a JAWS paper of checkpoint schedules for adjoint simulations here available. And checkpoint schedules is now incorporated in PyAdjoint. PyAdjoint is a generic algorithm and differentiation framework. So provides a tape-based approach to record the forward solvers. For instance, here I have the forwards, this nonlinear Burgers equation, and associated to this equation, we have this kind of tape. We have operations here, blocks. For instance, nonlinear solver depends of some, there are some dependencies as boundary conditions, forward state variable, mesh. And now PyAdjoint supports checkpointing. So we can use checkpoints with PyAdjoint, with checkpoint schedules package. So here an idea how was implemented checkpoints in PyAdjoint. So for instance, we have here this example, 5 time steps, and the checkpoint algorithm gave some instructions as store only the first and the step 3 in memory and run or disk, and we can do that in PyAdjoint. So basically, you have this tape related to these 5 steps, and then when the checkpointing algorithm give the instruction, save the first step, dependence, we have here this horizontal blue line, and everything that's a line that's touching here, will be stored in run or disk, depending of the checkpoint algorithm. The same here with the step 3. So at the step 3, every line touching here, will be stored. And then we have some another basic instructions as run the save the latest step for the adjoint computation, and basically we save the outputs of this tape in run and then we can, with this data, we can back and compute the adjoint. Fine. So now we have checkpoint schedules, but incorporating PyAdjoint, you can use, because PyAdjoint is a generic automatic differentiation framework. And here is an example how we can use in Firedrake, but that's very familiar for you. So we are using some symbolic, so we use UFL as well. So we import checkpoint schedules, some schedule from checkpoint schedules. We annotate our forward solver, and then we have our forward solver here. We have here, we need to have, I'm solving a time step problem. We need to have this kind of, this code line. So my tape, time stepper, and then the input here is the number of time steps, the time steps range. And then I have to enable checkpoints. The input will be the schedule provided by checkpoint schedule. And then I can compute my forward solver, tape it, and then compute the derivative using PyAdjoint. Yes. So, right, checkpoint schedules is a Python package, provide a common interface for a range of checkpoint algorithms. Can be incorporated in discrete and continuous adjoints. So for instance, I have a documentation where I implemented the adjoint there. I implemented in checkpoint schedules. I have a documentation. And it's easy to incorporate. So, and was also incorporated in algorithm differentiation, PyAdjoint. So the PyAdjoint users can benefit from the checkpoint algorithms available there. Find some reference here. Checkpoint algorithms and so here our peer-to-peer published in JAWS related to checkpoint schedules. Thank you. That's it.